All right, for those of you who are joining us via computer or video today, we are covering magnetism, electromagnetism, and then transformers. More than likely, we'll stop this video after we're done with magnetism and start another one on transformers, just depending on our length of time that we take to cover it. Magnetism is a very, very interesting force. That's what magnetism is it's a force. A lot of times people, when you ask them to describe magnetism or define magnetism, they're loss of words. They don't even know how to begin. They can tell you the effects of magnetism. Oh, it'll move, it'll stick to metal, or it'll make metal move, but they really don't know how to describe it, let alone actually understanding what is causing it. It is one of the principles of nature, like gravity, for instance, that we still don't truly, deeply, and thoroughly understand the cause of it. Um, One of the things um, that is surprising to us within the last 20 years is the level of magnetic force that is achievable. Uh, we have scientists now wondering, of all the forces in nature, why is gravity so weak in comparison to magnetism? Magnetism is an unbelievably powerful force, and it affects so many different things. For example, let's look at the Earth itself. How does magnetism affect the Earth on a global scale?
Keeps
Anybody?
the solar radiation off of us.
Does what?
Solar flares and whatnot keeps the planet.
Do you know how?
Yeah, the spinning of the Earth causes to create an electromagnetic field.
Okay.
And that is disrupted to the waves, the electrical waves of the sun.
Okay, so if we didn't have that, what would happen to the Earth?
It would be battered by unparalleled amounts of ultraviolet radiation or just gamma rays.
It would burn. It would actually strip away our atmosphere, guys. Over time, the radiation that comes from the sun, instead of passing around the Earth like a shield that deflects a lot of that electromagnetic energy, it would pass closer to the surface of the Earth. It would impart part of its energy onto the atmosphere, and it would whisk away that atmosphere. It's why planets on moons that do not have a liquid core or a magnetic field around them for whatever reason, it's very, very rare for them to have any substantiated atmosphere, let alone oxygen or water or moisture in some way, because it's all stripped away. So we couldn't exist. Life as we know it on Earth could not exist if we did not have a large magnetic shield encompassing the Earth. The other thing is, as um, Joey pointed out, is some of those rays could actually be harmful to life. Now, I wouldn't go so far as to say like it would cook us or it would burn us, but it would increase the chances that those rays would knock our genetics off of normal and cause cancers for us. That's the reason that people who are exposed to high levels of sunlight throughout their life develop skin cancers. A skin cancer doctor will tell you it is not a matter of if a person will develop skin cancer. It is merely a matter of when. Will you live long enough to have that mutation happen on your skin? Other things might kill you first, but given time, you will have that effect. There's a whole lot of different energies that can be deflected or affected by magnetism. All right. Magnetism is caused by the motion of electric charges. When you have electric charges that are either in a line with each other or moving in alignment with each other, all of those forces gather together into one same direction. Then that force can actually be felt and affected. It'd be kind of like saying if I had wind that was blowing from all different directions at the same time, you wouldn't be blown just in one direction. You release a balloon, the balloon's going to go this way, it's going to go that way, it's going to go back this way, it's going to come back this way. All in told, it's really not going anywhere except just in circles. And oftentimes, the energies, let's say, in this table, that's exactly what happened. They are not in alignment with each other, and so therefore their movement of electric charges is not in alignment, and therefore they're basically just fighting each other. No end effect because they're canceling each other out. All right. Electrons circle the nucleus or the core of an atom. Their movement generates an electric current and causes each electron to act like a microscopic magnet. So if I have one little bitty magnet and then I have another magnet that's little, and I let the two of them come together, are their forces larger? Yeah, they doubled, okay, and that would continue. So if I had 10 atoms that were in alignment with each other, or I had 100 atoms that were in alignment with each other, the force would be 100 times or 10 times stronger whenever there was 100 atoms that had their electrons aligned with each other. So part of the magnetic force is how many of these electrons or electron fields are in alignment with each other. All right. Now, in alignment can be an interesting thing. Let's picture a solar system, for example. You have the center, the sun would be the nucleus, and you have planets that are circling it. Do all of our planets move in the same direction? I wasn't aware of that.
I'm pretty sure they all
I was
Oh,
pretty.
I'm thinking of spin. My bad.
orientation.
Yeah, they're all rotating around the sun in the exact same direction. Yeah, you're good. Okay. If I put another solar system directly on top of that one, another one directly on top of that one, and directly on top of that one, you could picture how part of the particles could be moving in one direction, or planets, and the one above it could be moving in an opposite direction, and the one above it could be moving in an opposite direction. If I can get all of those to where they're all moving in the same direction, especially at the same time, their effects would be magnified. All right. In most substances, an equal number of electrons spin in opposite directions, which cancels out their magnetism. That's what's happening in this wood right here. You have the electrons that are spinning in this direction, and directly above it is another atom or another element that the electrons are spinning in the opposite direction. So since they aren't all in alignment with each other within their movements, the effects of one atom are simply canceling out the effects of the other atom. So how do we align the atoms to each other? All right. Sometimes it is literally as simple as hitting a substance hard enough to knock them all into alignment. All right. There's instances where you can take ferromagnetic materials like two steel bars and hit them hard enough at the same time that you will generate a magnetic effect from them for a short time period. The other thing is you can use energy to align those elements. Um, all magnets have north and south poles. Opposite poles are attracted to each other while the same poles repel each other. When you rub a piece of iron along a magnet, the north seeking poles of the atoms in the iron line up in the same direction. The force generated by the aligned atoms creates a magnetic field. The piece of iron has just become a magnet. Okay? So I can use the force that is created by this magnetic field to align the atoms in a ferromagnetic or ferrometallic substance. The thing about it is, as soon as I take that force away, those atoms want to go back to their natural shape. It's why if I have a magnet and I put it at the end of an iron bar, the whole iron bar just became magnetized, and I could pick up things with the tip of that iron bar. I have extended the magnetic field. But if I take that magnet away, will any of the magnetic effects remain in the iron bar? No? We'll have to test that one whenever we do our lab. Actually, they will. It will remain in there, but it will degrade over time. hate to use the word memory, but metals have a memory. Think of a spring. You move in one direction, as soon as you take the pressure off, it returns to its shape. Now, not all metal memories are as good as a spring. Depends on how they're heat treated and the alignment of their molecules. But most metals have some type of a give, a flexibility to it. And internally, those molecules can slightly rearrange, but it is kind of a crystal. All right. And so if you rearrange those too much, you can actually get cracks and fragments. Guys, those cracks and fragments are extremely visible using magnetism. All right. Mm-hmm. There's a test that's called like a magnetic flux test. So I have a big piece of metal like this table, and I need it to be flawless. Like I'm going to take this thing to space, and if there was the tiniest cracks or gaps in it, then it may have a failure point. I can hook a large magnet to it, and I can sprinkle iron filings on there. And if there is a crack in this piece of metal, the magnetic fields will separate at that crack, and it will be visible. So magnetism can be used to test for physical imperfections in very important or structurally important metallic objects. Magnetic testing is something that is done on those high and valued items a lot of times. Yes, sir.
Okay. Slap the chicken hard enough, I can make it magnetic. It takes 3,700 miles an hour to slap the chicken. If I slap it harder and faster, I can ionize it.
So, I think that if you slapped it that hard, you would actually make the particles of the chicken disconnect each other. It is definitely possible to turn almost anything into magnetism. Do you think you can turn yourself into a magnet? How?
It's possible because I have electromagnetic systems within myself.
Sure. If I took a balloon, I could actually magnetize you enough that the balloon would stick to you. You can do it in your hair. Okay, that's part of what static electricity is. Is the electrons are organized in such a way that they have an effect. All right. So you cannot separate the north and south poles of a magnet. I've got some magnets in my office that I use. Grab those real quick.
They were bred to die anyway, so why not see if I can make it a magnet while I'm at it? Yeah. Magnetized chicken? I don't know what.
Alright, so I will tell you guys when we are playing with magnets in this class, keep them away from your electronic devices. Don't get it near your cell phone. Do not get it near your computer. It will mess up electronic devices pretty severely if you're not careful. It's one of the experiments that we've done in the past. I believe last semester I had a desktop computer in here that was old that my mom was donating to a food pantry. Basically, to just get recycled. We fired it up and we saw how close to the motherboard and the processors we'd have to get these magnets before we could make the screen turn into rainbows. And it's actually pretty close. You had to get it pretty close. It surprised me. Now you could make the screen go black, but to actually nope, you've ruined it. You had to get it pretty darn close. But yeah. So a lot of our data is stored via magnetic signals, and so that data is what the computer operates off of. If it doesn't have its magnetized ones and zeros, it doesn't know what to do. Well, if you get the magnet close enough that either the reader of the ones and zeros can't read the ones and zeros, or you physically make the ones and zeros disappear, then you have I'm losing the wrong word. I've got the wrong word in my head. I want to say decrypted, but that's not the right word. You have contaminated. That's not the right word. I'm missing the right word. But you've contaminated your ones and zeros to where it's no longer in a usable format, and so it's no longer going to allow the computer do to work. So, do what? Give your phone cancer. So I got a magnet here, got a lot of magnets here, but when they're all stuck together like this, they might as well be one magnet. If I take them apart, do I just have the north and I just have the south? No. As soon as I separate them, no matter how small, even to the smallest individual piece, I still have a north and a south pole in here. Now, if I was to cut this in half, I'd still have a north and a south pole of each of those also. Now, there's some situations like that when you try to cut a magnet, you damage it and you will make it no longer be a magnet. What you can't do is only have the north or the south. They are the yin and the yang. If you take one away, it just looks like a teardrop. It's not the same thing. You cannot have a northern magnetic field without a matching southern magnetic field. Right. What do those fields look like? Those fields are not visible to the naked human eye. So we must add something on to that field which would allow us to see it. Metal or iron filings or shavings are the easiest thing. In other words, if I had this magnet and it was sitting on my desk right here, and I took iron filings and I sprinkled over it, they wouldn't just randomly fall here. They would fall upon the pattern of these concentric rings. The farther that I go from my magnet, is my magnetism stronger or weaker? Weaker. All right. And that is an exponential decrease. But theoretically, guys, this magnet's fields extend to infinity. Like, these magnet fields go all the way to Jupiter. Now, they're so weak by the time that they would get there that they wouldn't have any real effect. And they're so muddled because there's so many other magnetic fields. But theoretically, they just simply get weaker and weaker and weaker the farther out that you go. Eventually, you go far enough away, and they're not measurable by the human experience or equipment, and they will no longer have physical effects because they're too muddled. All right, but that also means the closer, the stronger, the stronger, the stronger. It's why even though one of these magnets individually isn't very strong, try to take one individually off the whole, and it is shockingly strong. All right, because it's attached. It is physically close to each other. So their strength is stronger. Now that magnetic field can be extended also through anything that is ferromagnetic. So if I would put a non-metallic piece of metal onto the end of this, it would align the molecules within that ferrometallic material and turn it into a magnet. When I pull it away, some of those are still in alignment with each other, and that magnetic force will continue. But over a short time period, minutes, for sure hours, they will reduce in strength because they will return to their non-alignment shape. All right. So how do we take and keep them in alignment? How did the material in, let's say, a naturally occurring magnet that you find on Earth, how did those molecules get aligned with each other? What makes a natural magnet? Anybody know? Pressure? Not normally pressure. What?
It's spinning really fast?
No. No. So in ancient times, they called them lodestones, and they were almost exclusively found where lightning struck. When you have a large electrical force that passes through metal, A, it can melt that metal, and B, if the electrons were aligned as that metal cooled, then those electrons or those atoms, those molecules would remain in alignment after cooling. It's also done by cooling metals that are exposed to the Earth's magnetic force. So the Earth's giant magnetic force is actually aligning certain metals as they're cooling. It's part of the way that we can date certain past organic material. Let's look at an old tree. When a tree takes water in, it also takes in iron because iron can dissolve into water. And then as the tree uses that iron in its cells, we can actually look at that alignment and see like a dating process of when did this happen? All right. So we can tell based on these events that the Earth's magnetic field actually reverses. Like what we know currently as the North Pole has been the South Pole in the past. And it is rather concerning to scientists right now that our poles are moving. Poles have always moved in kind of a natural little circle, but right now that's not just happening in a circle. It's moving at approximately 50 miles per year towards a flip. The North Pole is moving towards the south, and the South Pole is moving towards the north. Now, there's a real indication that this could have devastating effects on the globe if our poles were to rapidly shift. What effects might we have on Earth if our magnetic poles were no longer here or were to shift? How could it affect life on Earth?
The
The water would go into weirder places. Water isn't life.
well, like water moving, right? Mass amount of water. Because our planet's 75% water. So,
Sure, but water is relatively unaffected by magnetism.
but,
How about on life? Does life use magnetism?
yeah,
How?
birds and their migration patterns.
Navigation, guys. Even humans have
Aviation.
do it.
Aviation.
Yeah, have a natural sense of direction that some people believe is based on the magnetic poles of the Earth. But there's no doubt about it that birds, insects, bats use the magnetic poles of the Earth for navigation and migration purposes. If suddenly the geese couldn't tell which direction was north, they wouldn't be able to migrate, they wouldn't be able to reproduce. And in just a few years, we would have an environmental devastation of what do you call it, mass extinction proportions on our hands. All right. So magnetism and the Earth's magnetic fields are extremely important to us. Whenever you have two magnets that have opposite poles, they attract. Whenever you have two magnets that have similar poles, they repel. Whenever we talk about the strength of these magnets in relation to their distance, it is much easier to learn about this on the repelling side. Look at it this way. I can push these two together without a problem from this distance. Hardly any force required. But the closer and the closer and the closer that I get to this, I don't have the physical strength to make them touch. Eventually, you get to the point of it will lift a train. That's what a mag lift train is elevated by. They have magnets on the tracks that are north. They have magnets on the bottom of the train that are north. As the train wants to sit on those magnets, it never touches. It is magnetic lifted. Therefore, there's virtually no friction between this train on the tracks. There's nothing that is physically touching. It is floating. And guys, you can use a series of magnets to make an object float in the air. All right. Electromagnetism. While some substances can be magnetized by an electrical current, others cannot. All right. When electricity runs through a coil of wire, it produces a magnetic field. The field around the coil will disappear, however, as soon as the electric current is turned off. Guys, when I have electrons that are flowing through a wire, they are all in alignment with each other. They're all moving in the exact same direction. And they create a magnetic field around the conductor. Whereas in my previous slide, the magnetic field is created on the sides and in the 3 dimensions around this magnet. Same way if I've got this. I've got a magnetic field that is all the way 360 degrees around this magnet. Starts here, goes out, comes back to here, goes all around it. If I have a conductor, let's say, well, I've got a conductor right here. Here's my conductor, and I've got electrons that are passing through this conductor. I have a magnetic field that forms around this conductor, and it extends the full length of the conductor. So if I had a conductor and it ran from me to Samson, and I passed electricity through it, the field around that conductor would be basically identical from here all the way to Samson along the conductor. But I can amplify that by using coils. If I have coils of this wire, that magnetic field around this conductor is right next to another one, right next to another one, right next to another one. They are amplified. Just like if I take this and I put all these together, I'm amplifying the magnetic field. Now, the moment that those electrons stop flowing, that magnetic field collapses. All right. What if those electrons begin to come back the other direction? Instead of passing from me to Samson, they reversed and they started coming back this direction. The magnetic field is going to disappear whenever they stopped. And then as soon as the electrons come back, I'm going to have the opposite magnetic field created. So if I've got electrons in another wire that's going this direction to Samson, and one that's coming this direction from Samson, I actually have different polarities, and they would attract to each other. It's one of the reasons in conduit's the stuff on the wall up there that electric lines run through. It is against code to have AC electricity and DC electricity in the same conduit. Because AC electricity, the electrical direction changes 60 times per second, which means the magnetic field around that conductor changes 60 times per second. Well, if I had another wire laying in that conduit, every time that the magnetic field would change, it would cut through that other conductor and it would affect the voltage in that conductor. You'd actually be able to watch your voltage go up, down, up, down, up, down, up, down, up, down on a DC circuit if it happened to be laying next to an AC conductor that was conducting electricity. All right. Now, I will remind you, voltage is not what we're talking about. I could have all the voltage in the world between Samson and myself, but if I didn't have the flow of current, then I wouldn't have created that magnetic field. It is the actual flow of electrons that creates the magnetic field. Remember, though, that the field around the coil will disappear as soon as the electric current is turned off. Now, how strong that magnetic field around that current is also proportional to the amount of current that is flowing through. So if I have 1 amp flowing through this wire, or I have 10 amps flowing through this wire, the magnetism that is going to be created, the electromagnetism, would be noticeably stronger for 10 amps of electrical current passing through. All right. Guys, we can create magnets using electricity. You ever seen the device at the junkyard? It's like on a crane. It goes down to a pile of metal, and suddenly all the metal shavings just like float up and attach to it. That is an electromagnet. A person inside the crane or the equipment can hit a button, pass electricity through that piece of metal there, create magnetism, pick up metallic objects, and then when they're ready to drop them, he turns the magnetic field off by stopping the electrical current from passing through it. As soon as there's no electrical current passing through there, there is no longer a magnetic field. Because when that metal jumps up off the ground and elevates itself into the air, that's a powerful thing. That movement is basically the same thing that an electric motor does. But instead of having it just go from the ground up and stop, it's doing it in a rotational cycle. Right? And that rotational energy can be put to a tire, and that tire touching the ground can have traction, and we can use that same concept of electromagnetism to move our electric cars down the road. On Wednesday, we're going to make that. You guys are going to get a battery. You're going to make a device that will actually turn electrons that are flowing from one side of the battery to the other into electromagnetism, and then turn that electromagnetism into motive force. The Earth is a magnet. Scientists think that the molten metal that is in the core is spinning. It is moving. Earth's outer core generates electrical currents. The currents create a magnetic field with invisible lines of force between the Earth's magnetic poles. All right. That spinning iron core is what is creating the electromagnetism through the crust, which is in effect having a giant magnetic force field that is created around Earth. Electromagnetism is discovery. I really love this story. I don't know if you guys did your reading or not, but if you did, it talked about a person named Hans Christian Orsted. I just remember him as Hans. He's a teacher, like me. That's why I like this story. All the way back in 1820. Now we say that because that was really not that long ago. When you think about things, like we understood how to use a magnetic compass for a real long time. All right. Why we didn't connect the dots that electricity and magnetism had something to do with each other until 1820, I don't know. But it was an accident. It was an accident in a class lab. This gentleman had talked about the possibility of electricity and magnetism being related to one another. And in the process, he accidentally demonstrated to his class that it conclusively is. What he did is, by passing an electric current through a metal wire suspended above a magnetic compass, he was able to produce a definite motion of the compass needle in response to the current. What began as conjecture at the start of the class session was confirmed as fact by the end. Like right now, if we suspected that temperature was able to affect the voltage output of solar cells, but we really didn't know it, and a cold front moved in, and suddenly, in a matter of seconds, the voltage went up when my solar cell got cold. It'd be like, wow, why did we never try this before and prove that it had an effect? But literally in class, he was like, well, I kind of think that magnetism and electricity have something to do with each other. He happened to have a compass. He set the compass on the table. He passed electricity through the coil above it, and he watched the movement on the compass needle. Well, obviously, if you can move a magnetic compass using electricity, then electricity and magnetism have to be related with each other. And as soon as that was proven that they were related, that opened up a whole another world of study and trying to understand electromagnetism and the effects that it has on the world around us. All right. 1820, that's 200 years ago. That was it. Now, again, in our small lifetimes, that seems like, oh, that was a long time ago. In reality, think of the improvements and the effects of electromagnetism. We couldn't have a computer. We couldn't have a cell phone. We couldn't have an electric motor as we know it if we didn't have the basic discovery that electricity and magnetism are related. Life uses magnetism, guys, in all kinds of ways. Some animals, such as pigeons, bees, and salmon, can detect the Earth's magnetic field and use it to navigate. Scientists aren't sure exactly how they do this, but these creatures seem to have a magnetic material in their bodies that act like a compass. Studies have shown that magnetism had a significant positive effect on plant growth. Plant seeds under the influence of the magnetic fields had a higher germination rate, and these plants grew taller, larger, and healthier than those in the control group. No adverse effects of magnetism on plant growth have ever been noticed. Guys, it's very, very a commonly held belief, but not necessarily proven, that because we, as in life, evolved under constant magnetism, that it affects us a lot more than we think it does. There is healers that use magnetism for healing properties, especially in the Eastern medicine. Um, for example, there's magnetic bracelets that golfers and athletes wear that swear that magnetism close to their body removes arthritis pain and tennis elbow and other negative impacts from aging and um, um, from injury. That's where I was going with it. From aging and from injury. There are also claims of effect on magnetism and healing, that strong magnets or exposure to strong magnets increases the rate at which humans heal. All right. There is also proof of removal of toxins from the body using magnetism. Um, Again, I'm not a doctor. I'm not trying to sell any of these concepts or ideas. What I do believe is that we are affected by magnetism, and strong levels of magnetism and weak levels of magnetism both are going to affect us. I believe if you live near a substation, the magnetic fields that are generated around that substation could potentially have birth defects on sperm and eggs and the developing child in a womb. So it's the only thing that I will tell you is, if you as an adult want to have kids, do not live next to a power substation. The magnetic fields around those will affect you, without a doubt.
Do you want to study on that?
I don't have the time for that.
I was gonna say I have
Yeah.
arthritis.
Yeah, there's I'm sure that there are studies that have been done on that. The one that made me be worried about that is whenever cell phone towers are put in, you're not allowed to put cell phone towers in within 500 feet of a school because of the electromagnetism that is emanating from the cell phone tower. If the government won't let us put these near schools, that's an indication to me that there's probably some scientific testing that says that it impacts our development, physically or mentally. So, guys, your thoughts are basically, yes, yep, electromagnetic pulses that are moving through different neuron patterns in your brain. So,
if the government wanted to, they could read your mind.
they already can if they would get an MRI on you. So we already have the technology to put a device on people's brains, and I hate to use the term read their thoughts or the phrase read their thoughts, but we can accurately depict what their thoughts are, including dreams. So what it kind of goes down to is, every time that you have a thought, the electrons that pass through those neurons, those neuron pathways in your brain, they actually send out a signal. If you had the exact same thought over and over and over again, that signal would be very similar. And so we just need to train a receiver to pick those signals up, put them into a format that we could relate to or understand, that basically we are reading brain waves. All right? That's not beyond the existing technology. But they can't do it from a distance. They don't just get to shine a light at Donnie's head and be able to tell what he's thinking. Not yet, and that's exactly right. But that's whenever I went back and said that this is extending forever. There is a little bit of study on this, on yawning, and I'm going to call it pseudoscience. I really don't want to call it true science. If I yawn right now, you guys have experienced that it's contagious, right? What if I told you there's studies that put two people in rooms that couldn't, the thought made you yawn? Okay? Literally, the thought made you yawn. That you could put two people in isolated rooms from each other that can't hear or see each other or smell each other, but when one yawns, the chances that the other person is going to yawn in the very near future goes up dramatically. And there's some serious thought that it developed as a as a group cognitive action, that when you yawn, it symbolizes something is going to change. Like, hey, we're all tired and we're going to go to bed. Or we're all sleepy from sleeping and now we're going to wake up. Yawns symbolize a change in activity level. And that it's not the sound, it's not the sight, it's the thought. And that thought is actually passed through electromagnetic signals. When I have the thought of yawn in my head, if we all grew up with the same thought of that's a yawn, then that's kind of a universal thing. We all kind of understand it. We don't have to speak it or hear it. We can don't even have to see it. We can think it, and it happens. And so there's some people that believe that that thought pattern can actually be transmitted through walls, through anything that electromagnetic symbols could be passed through, and you could pick that thought pattern up. There's also thoughts that go on that goes farther. It goes on to emotions. Have you guys ever experienced that you've been in a pretty decent mood and you get around somebody and suddenly your mood is bad because they had a bad mood? Or how about the opposite? You were in a bad mood and suddenly you got around somebody and they just put you in a good mood. They didn't say anything to you. They didn't do anything to put you in a good mood. It's like their mood literally transferred into your brain. There is there is some pseudoscience that says that's electromagnetism that is catchy. All right. Um, as far as most life forms are positively impacted by magnetism. I'm sure that there is a certain level where it becomes negative, though. Yeah. It's a natural force for thousands of years. We have been fascinated with magnetism. Let me tell you about some scams. So I got a piece of metal on the table, and I put my hand under here, and I can make things move. I'm a witch. Give me your money. Okay. Um, these processes for uneducated individuals seemed like magic, and it was exploited by the people who did understand the processes. All right. Eventually, it went from exploitation to science, and we began to make significant improvements in our technology using magnetism. The ancient Greeks and Chinese knew about naturally magnetic stones. They were called lodestones. If you've never heard of a lodestone, now you have. There's a lot of interesting mythology and legend. That's the term. Legend centered around lodestones. These chunks of iron rich minerals were magnetized by lightning most of the time. The Chinese discovered that they could make a needle magnetic by stroking it against a lodestone, and that the needle would point north and south. It would align with the magnetic fields of the earth. So they, being the Chinese, were able to figure out that one naturally occurring magnetic material could pass its properties on to other magnetic materials if they had that capability, like they were ferromagnetic material. Is you can't magnetize aluminum. It doesn't. It's not a ferromagnetic material. All right. So only certain metals can become magnetized. Maybe if you slap it hard enough, you can magnetize aluminum. Nowadays, guys, it's used for thousands and thousands of purposes. We don't have near the time to cover all the purposes that magnetism is used for. Navigation is one of the oldest uses of magnetism, though. We circumnavigated this globe using magnets. To turn things on, a relay is a magnetic device. If I pass electricity through a coil, it creates a magnetic field. If I have something that is attracted to that magnetic field, I can move that something and open or close a switch using magnetism. Why would I want to do this? Well, guys, if I reached over and used my hand to physically close this, I'm exposing myself to electricity. All right. However, if I use a magnet to close this, there is no real chance that the electricity could pass through the magnet and electrocute me. So it allows us to turn large loads on and off safer. All right. One of the biggest examples of this is the starter in your car. When you turn the ignition to on, it's not starting your car. It's just turning all of the electronics within your car on. You turn it farther to start your car. What you're actually doing is you're engaging a solenoid. That is a little coil that once it is energized with a small amount of electricity, it creates a magnetic field. That magnetic field closes a circuit. That circuit is connected directly to your battery, your starter to your battery. So when you turn the ignition in your car, you're not actually completing the circuit through your ignition to your starter. That would require great big wires because there's a lot of electrons that flow from your battery through your starter and back to your battery. Your ignition in your car could not handle that amount of current. All right. How much current does it take to start your car? Well, how much current will your battery output? Anybody? It's called the cold cranking amps. We just talked about it like last week whenever we were discussing batteries. 48. No, that would not start your car. Most batteries that are SLI, starting, lighting, and ignition batteries, you're going to put out 500 or more cold cranking amps. Like my little Honda Civic required a battery with 550 cold cranking amps. My Honda Pilot requires one with 750 cold cranking amps. Some batteries today can output 1,000 or more cold cranking amps. Guys, to have 1,000 amps pass through a wire, you're going to have really big wires. That's the reason that the starter cables on your car are really big. They're bigger around than your thumb normally. All right. You're not having all of that amperage pass through your ignition in your car. You're having that amperage pass through a solenoid, a whole separate device that when you turn the ignition, a small amount of electricity is used in to form magnetism. That magnetism is used to close a circuit. That circuit makes your car go, and as soon as it started, you disconnect the solenoid, which then opens the circuit. All right. Um, that would be called a relay. There are some relays that have multiple contacts. In other words, whenever I wanted to turn multiple things on at once, instead of walking along and flipping on lots of light switches, I could flip one switch, which would activate a solenoid or a relay and turn lots of switches on. Why wouldn't I just put all of those devices onto the same electrical circuit? Well, a lot of times because they go to all different kinds of things, they're all different sizes, and you could not have that quantity of current passing through one circuit. Let's say I have a conveyor belt, and this conveyor belt runs through the whole factory. There might be 30 different motors that run that conveyor belt, but I want the whole thing to come on at once. Well, if I switch one light switch and it's going to power all of those, the wires would have to be huge for that. However, if I switched one light switch and all it did is need to turn a magnet on, and that magnet would turn on all of these other different switches simultaneously, then they're all on different circuits, but I can activate all of those circuits using magnetism. And more importantly, I can do it very safely. The switch in which I'm messing with might only be 0.1 or 0.2 amps of current. at 120 or 240 volts. So it's much, much safer. All right. Um, Magnetism is a force, and I need you guys to recognize and remember that magnetism is a force. Um, Electromagnetic induction is the next thing that we're going to talk about, and I think that it's a good stopping point right now because we've been recording for about 50 minutes. But before we move on to electromagnetic induction, we need to do our best to understand magnetism. What is magnetism? It's a force. What causes some things to be able to be magnetized, but other things not to be able to be magnetized? The alignment of their electrons. If their atoms are aligned to where the electrons are moving in the same direction as each other, then they're going to work together. If they are moving in a way that they are not in alignment with each other, let's say they are perpendicular or they are actually the opposite direction, then the effect of the movement of those electrons will counteract the movement effect of the other electrons. Therefore, there will not be able to be a magnetic force that is created or exerted. All right. Earth's magnetic field is moving. All right. That's one of the other things that you want to know. All right. Questions over magnets? All right.